Hey, well, welcome back. My neighbors are getting a little squirrely. So today we're going to take a look at box and whisker plot. Okay, a box and whisker plot tells us a lot of the same information that we learned about in a cumulative frequency graph, but they're a lot easier to draw. So I don't know if you've ever seen a box and whisker plot. This is what they look like. There's a box, and then these two lines that run out to the side, those are referred to as the whiskers. Now, I first learned about these back in 1990 when you guys were still just a little sparkle in your daddy's eye. Um, and I had never heard of them before. I was teaching sixth and seventh grade math in Frederick, Maryland. And the new standards came out and they said, we got to teach box and whisker plots. And I'm like, box and whisker? I've never even heard of that. Well, they're very convenient. It's a good way of expressing information because what it does is it breaks the information up into 4 parts, just like your 5-number summary does. All right, so when we take a look at a box and whisker plot here, all right, this middle number or this middle line, that's our median. All right, this line on the right side of the box, that's your 3rd quartile value. Okay, the line where you put the left side of your box, that's your 1st quartile value. And then this is your maximum value. This is your minimum value. And when you subtract these two right here, that gives you your interquartile range. Now, when we talk about percentages or percentiles, each part of this box represents 25% of the data. So from the minimum to the 1st quartile is 25% of the data. Okay, now this is the data that we did on the heights of students. So that's about 156. So we could say that 25% of the class is shorter than 156, or we could say that 75% of the class is taller than 156 centimeters. All right. The next one, that's another 25% between these two marks. That takes us up to the median. So 25% of the students fall between 156 and the median was around 160. From 160 to the upper quartile, Q3, okay, that's another 25%. Now you'll notice that these two areas aren't the same. So the space between the median and the lower quartile is a little bit shorter than the space between the median and the upper quartile, even though they contain the same amount of data. So what that tells you is above the median, the data is more spread because that's part of the box is longer. So what a box and whisker plot tells you is just by visually looking at it, it tells you sort of, is the data spread out? Is the data compressed? That's one real strong quality of a box and whisker plot, as long as you know what you're looking at. And then the fourth part is the upper 25%. All right. So what we used to do is we would take these and we would draw them for a test grade. and this would be the low grade, this would be the high grade, then our different quartiles. And then students would put an X where their grade was. So let's say that I graded right there. Well, that just told me visually that, hey, I did better. 75% of the class scored lower, all right, 25% scored higher. So we referred to that as a percentile. All right, now the next thing is this graph right here, like I said, shows us the same thing that we get when we do our histogram, right? And actually down on this graph, I've got it superimposed on the frequency, the cumulative frequency diagram that we did on Monday. All right, so let's see how we draw this in Geogebra. Okay, so I've logged into my student Geogebra account. And here was the chart that we've been working on. Now, if you're not able to change anything in here, what you have to do is click on these three dots and say open up in the app. And now you can manipulate things. You got your spreadsheet. So I'm going to highlight my heights. I'm going to click on the bar, go to one variable analysis, and I'm going to change that. See, I had a histogram. That's what we did last week or Monday. Now I just go to box plot, and there's my box plot. Okay, there's my summary data. I can click, close these down. You can always resize these windows. It's like sliding doors, sliding patio door. Okay, I want to put a grid up there so I can see it a little bit better. Okay, and that's our box and whisker plot for that. Now, if you want to compare this with another type of graph, you can go up to here where there's these, it looks like an equal sign, and that says show second plot. So down here, I could do my cumulative frequency diagram. So I'm going to click on histogram. Okay, go to the gear. I am going to set my classes manually. So if I remember correctly, they were 149.5, and the width was 3. And then I'm going to go down here to frequency type, make it cumulative. And then if I want the actual curve, there's my curve. And I can put a grid on there, and there's my other graph. So now I can look at these two graphs together and be able to compare them. Now, right now, these numbers don't line up, okay, but you can adjust this so that they do. So all I have to do is just close these windows on the right. So just click that, come over here, click that, gear closed. And it looks pretty good that this 150 is lined up with that 150, fairly close. And now I can see the data. Now, if we had done the lines like we drew on Friday or on Monday, we'd see that the 50 percentile would be the same as the median, etc. So box plots are much more user-friendly to make than cumulative frequency graphs. So here's another picture of a box and whisker graph showing us the different portions of it, that it gives you a very straightforward visual way to see how the data is spread. All right, gives us an idea of what we call the range of the data. So we can see here that this is the 50th percentile. So that means 50% of this data is between 12 and 16. Okay, 50% of all the values. And they're close together, so they're fairly bunched. Now, if we go to the next part of the graph, to the right of the median, we've got 50% more of the data, but you can see by the length of this that it's much more spread out. So, for example, this could be an example of, let's say, a marathon race. Or not actually, this would have to be like an ultra marathon, because we're talking about 13 hours here, 31 hours. All right. So the most competitive runners in this particular case are going to be the fastest runners. So this would here, if you notice, this is 25% of the data is in that little whisker, just between 12 and 13 hours. 75% of the data is above that, but there's still 25% of the people that ran the race are in this little range. So this would be your like very competitive runners. 25% of the people that ran the race fell in this category. Right? 50%, 25 here, and then another 25 here, ran the race in over 16 hours. So basically, you have a race where you've got people that are really competitive, and then you've got this long tail of runners based on how fast they're able to finish the race. So this could very well model a situation like that. All right, another advantage to a box and whisker plot is that it gives you a very quick way of determining whether or not the data you're looking at is normally distributed or if it's skewed one direction or the other. Now, when we talked about skewed data, we're talking about the mean is being skewed. So what would cause the mean to be skewed? Well, let's say, for example, we took the heights of everybody in our class. Yet there was one person in the class that was 8 feet tall. Well, what that's going to do, that is going to skew the mean. It's going to take the mean and it's going to make it larger than it actually is. All right. So, and then if you took the average or the mean of the heights in the class, yet there was somebody that was very, very short, then that would affect the mean. It would make the mean appear lower than it really is. So that's why the mean is not used a lot of times in terms of describing data, because very large values and very small values can affect the mean. Those big and large small values are called outliers. And box and whisker plots have a way of identifying what data would be considered an outlier, but more of that in a second. All right, so let's say that these were just heights of people in general. Okay, basically what this is representing is that most people are going to be somewhere close to the average. That's this 50% right here. Then you're going to have a few people that are very tall. So this is the majority of the people. And then you're going to have some very tall folks. And then you're going to have some very short folks. And then you're going to have a few that are shorter than most, but still taller than the shortest. And the same thing over here. Okay, this type of curve here is referred to as a bell curve because it looks like a bell. And it's used to represent data that is normally distributed. Now, when data is normally distributed, the mean and the median and the mode are the same or very close to each other. So this is the median But if since it's normally distributed data, that number is also going to be very close to the mean. So in normally distributed data, the mean would be a decent value to use to describe the data, or the median would be. Okay, now what happens is if you had someone that was especially if it was a small sample like our class, 17, 18 kids, and if one person is 8 feet tall, then the mean of that class is going to get shifted to the right. All right. If we took our class, but let's say that I had, there was a cat that was one of my students. So the height of that cat is, when I add that height into the sum of all your heights, then it's going to take the median because it's very short, and it's going to move the median. It's going to skew it over here to the left. So what that does is that changes the shape of our bell curve. All right. So if you look at a box and whisker plot and it's symmetrical like this bell curve is, then this is telling you that the data that we collected and plotted is pretty close to being normally distributed. This is nice and symmetrical. The two halves of the boxes are the same. The two whiskers are close to being the same. So it gives us an idea that this is fairly representative or normally distributed data, and the median and the mean would be about the same. All right, so a positively skewed means the median moved in the positive direction. So that would be caused by a few people being, let's say if we were using the context of height, if we had our class of 17 students and two of them, we had an 8-foot person and a 7-foot person, then what that would do is that would move the median in the positive direction. It would move it in this direction. So our box and whisker plot would look like this. So it's sort of counterintuitive. When you think of positively skewed, the big hump of the box, or my normal curve, actually the hump moves in the negative direction because the mean moved to the right. So here's an example of that. When data is skewed to the right or positive, if you notice, the mean moved to the right of the median and the mode. Whereas when it's normally distributed or symmetrical, they're all fairly close to being the same. And the bell of my curve actually moved opposite this direction. So this would be if we had in our class a few really tall people. That would skew the mean to the right, and our data would look like this. So our box and whisker plot would end up being, this would represent the same type of skewness. All right. Now, let's say that we had our 17 students, but 4 of Snow White's dwarfs came to and were in our class, and we did our heights. So now their height is going to take the mean and move it in the negative direction. So the bulk of the students still are going to be to the right, but this tells us that our mean got skewed to the left, or this is a negative skew. So it would look just like the other one, but the box would now, let's see, where's our median? Look something like that. So this is negatively skewed data, positively skewed data, and this has no skewness to it. And it all has to do with there being values that affect the mean and move it one way or the other. The mean is very susceptible to very large data points or very small data points. So to review, this is the box and whisker plot for normally distributed data. Down below here is a box and whisker plot where the data is positively skewed because the mean got shifted to the right. And then here is a box and whisker plot that exhibits negative skewness. So the mean in this case moved to the left, creating a skewed data distribution. Outliers are unusual data that you might have in your set of data. And there's a simple rule that we can use to determine whether or not something is an outlier. Typically, if it is an outlier, okay, it's going to either be a maximum or a minimum value. We don't plot it as part of our box and whisker plot. We would show it where it is, but we would put an X instead of using a dot like we did here. So then if I had an outlier, it would be represented like that, and then I would go to the next largest data point, the one that's closest to it that is not an outlier, and then that would become the max that I would use in my drawing. And then the same thing's true if I had a outlier that was a minimum. Okay, I put an X to show that there was an outlier there, but in order to avoid it skewing our data, we're not going to include it in our box and whisker plot. Now, the way that you find or you identify an outlier is using the interquartile range. So on our graph here, this is the first quartile, there's our median, and here's our third quartile. If I subtract these two values, 15 and 21, I get an interquartile range of 6. All right, the basic rule is you take 1.5 times the interquartile range. So the interquartile range would be, is 6. I multiply that by 1.5, I get 9. All right, something is an outlier if it is 9 places further than the third quartile. All right, so my third quartile, on an outlier would be greater than, my third quartile was 21. If I took 21 and I added 9 to it. So any value greater than 30 would be considered an outlier. So this data point, we would mark with an X, and then we'd find the first data point in our set that is smaller than 30. And then we would use that as our maximum. All right, on the low side, an outlier is going to be smaller than the first quartile minus 9. So my first quartile was 15. 15 take away 9. Any small or lower end quartiles would be anything that is less than 6 would be considered an outlier. So this data point of 11 is not an outlier. Okay, and that's how you avoid your data getting too skewed by extremely large values or extremely small values. So to emphasize, a common mistake is drawing your whisker out to the outlier. Okay, even if it's an outlier, you're not drawing your whisker out to it. Okay, you're drawing your whisker would go all the way to a value, not to the outlier, but to the highest data point that is not an outlier, or the lowest data point that is not an outlier. All right, that's it for box and whisker plots. I'll see you next time.